Okay, this is lecture 6 of our VLSI devices 2025. Today we will learn an important expression for electric field, surface electric field. So let me just briefly review our previous lecture. In the second last lecture, we have introduced a condition of a flat band voltage, and when gate bias is flat band voltage, then we have just a flat energy band diagram. So that was one thing. So if we apply certain gate bias voltage which deviates from flat band voltage, then since we have additional voltage to the gate side, now this is corresponding to the banding of our electron energy band. So how can we understand this energy banding? So what we can say is, okay, there was a flat band, and now we have certain amount of additional voltage, and this certain amount of additional voltage is converted into minus Q times Vg minus flat band voltage. Let's say that if we have a positive value for this voltage Vg minus V flat band, for example, let me just give you a concrete example. Happen to be our gate voltage is 0, and happen to be flat band voltage is, for example, minus 0.94 volt. Then although you apply 0 volt to your gate, actually this situation already gives you gives you positive 0.94 volt. So this is converted into what? Converted into minus 0.94 electron volts, because we must multiply minus Q. So it means that here, if this is corresponding to our silicon substrate, and if here we have gate voltage, gate terminal, then band bending, the overall band bending is corresponding to minus 0.94 EV. Yes, so that was our value. Let's say that here and there the difference is corresponding to minus 0.94 EV. So now our question is, our system is made of two different regions. One region is called as oxide, and another one is called as semiconductor, silicon, substrate, whatever. So here we have semiconductor part, and the overall band bending is given as this number, and it should be divided into two parts. One part is in its oxide region, and another part is in semiconductor part. So that's the reason why we can write down this important equation. Sometimes this expression is called as MOS equation, but name itself is not that important, but the equation itself is quite important. So please try to understand this equation. The left hand side term, that is corresponding to the overall band bending. The overall band bending is divided into two parts, and one part is, okay, the voltage across our oxide region. So this is corresponding to this oxide region, and the remaining one is the one applied to the semiconductor part. However, how can we express this band bending only inside the substrate region or semiconductor region? The quantity was called as surface potential. Although its name is surface potential, but it is not exactly the potential at the surface point. Instead, it is defined as the difference between the substrate and deep substrate and surface. So exactly this quantity is corresponding to the band bending inside our semiconductor region. Of course, if we say energy bending, then we must multiply minus q to phi s to convert into the EV energy scale. But well, we are right now just writing down all quantities in voltage unit system, so it's okay just to write down phi sub s. If we are really talking about energy bending, then we must multiply minus q to the left hand side and right hand side of this equation. But right now we are just using volt unit equation. Okay, so I think that understanding this MOS equation is quite important. MOS system has three different parts: metal, oxide, and semiconductor. However, in terms of voltage division, we cannot assign any non-zero voltage to the metal. If we assign non-zero voltage difference in metal part, then we will have current conduction inside metal. That is not allowed. So that's the reason why we neglect metal part. Then now we have only two parts. One is oxide and one is a semiconductor. Yes, so band bending is just divided into two parts. So once you understand this MOS equation, then the next question is, what is the unknown variable and what is the known variables? For example, flat band voltage. Do you know the flat band voltage at a given system? Yes, you know, because this flat band voltage is related to the work function difference between metal and semiconductor. Then how can you estimate the metal work function? That is given by the problem specification. When you use a certain metal, then that metal's work function is more or less given to you. For example, maybe you remember the value for aluminum. It was 4.1 EV. If you use aluminum as a gate metal, then your work function is 4.1 EV if you did it or made it properly. Another one is semiconductors intrinsic, semiconductors work function. However, that part is really dependent on the acceptor density inside your p-type substrate. So once you know the metal work function and once we know the acceptor density, then this flat band voltage itself can be calculated. So this is given known quantity. And another one, think about this one. Do you know gate voltage? When you apply 1.0 volt to your MOS system, then what is the gate voltage? Yes, it is 1.0. When you apply 0.5, then it is 0.5. Who decide the amount of voltage applied to the gate? You decided, oh, I will just change my voltage source and apply just 0 volt or 0.7 volt. So we have the full control over this gate voltage. So left hand side term of this MOS equation, all terms are known quantity. Then now think about this one here. When you have a look at this right hand side term, now you can find phi sub s. Phi sub s means that the band bending or potential difference inside the semiconductor, and this is potential difference inside the oxide. And both quantities are not known to us, so we have no idea about what is phi s and what is V ox. But point is, this is only one single equation. We have one equation, and what we want to know is how many unknown variables are there. There are phi sub s, surface potential, and oxide potential. Well, we have one equation, two unknown variables, so simply speaking, this is it becomes undetermined system. So in order to make it determined, we need another relation for these two quantities. Simply speaking, although this MOS equation looks beautiful, but we need another relation between phi s and V ox. What is this number? Of course, you can say that, okay, if we have, for example, if we have a certain band bending in oxide, and if we have another one corresponding to the oxide potential, then the sum of these two quantities will be given as, once again, minus Q times Vg minus flat band. However, I'm just repeating once again this MOS equation, so it does not give us any additional information. In order to make it determined, we need another equation, and that another equation is now shown here. So let me just do it together with you. Since this system has two different regions called as oxide and semiconductor, it has interface, and at interface we can define oxide electric field, the electric field inside oxide layer, and also we can define electric field inside the semiconductor. But let me just give you difference between these two quantities. Oxide field, it is just constant all over our entire oxide region. I mean that here, what is oxide field? Let's say that it is corresponding to 1 megavolt per centimeter. Let's assume this is quite a typical value. And if we have such kind of oxide electric field, and let's just a little bit change the observation point, then if I ask you what is the electric field, what is your answer? If you don't have any net charge density inside this system, then you should say that oxide field is still 1 megavolt per centimeter, because net charge density is the source of changing electric field. If you don't have any net charge density inside your system, your electric field cannot be changed. So simply speaking, inside your oxide region, oxide electric field is just one single quantity, so it's okay. Only one representation is enough. However, think about this semiconductor region. So can you say one single electric field fits all over your system? Unfortunately, it's not. For example, if we go too deep into the substrate, then obviously your electric field becomes 0. And if you go to the enter, if you enter just into this depletion region, then your electric field is no longer zero, but its magnitude would be very low. So if you go to further deeper and deeper into the substrate, then you will feel that, oh, magnitude of my electric field is increasing and increasing. Why it is increasing? So it suggests that there is something there is something to increase the electric field. What is it? As I told you before, electric field can change only when we have electric charge. When there exists electric charge, then we can band the energy band. So simply speaking, here we can find net non-zero electric charge for this system. So simply speaking, when you have a look at this tower 2.173, so you can see that here E silicon. It looks like a silicon electric field, but please note that silicon electric field is a function of position. If you have different position, for example, let's say that this is 0 and E silicon at x equal to 10 nanometer, so certainly they are not the same. Okay, so then how can you understand this equation? This equation should be interpreted as the electric field at x equal to 0. At a certain point, the interface point, we have to have continuity of what? Continuity of displacement vector. So actually it's a normal component, so that is given as this equation. Simply speaking, permittivity times electric field gives us displacement, and also permittivity and electric field, their product gives us the electric field. They should be the same. Are you with me? So now you can understand this quantity. Well, how can you express this Vox, oxide, the potential difference, or potential across this oxide layer? It can be easily expressed as Tox times Eox, because this is Eox is electric field is just gradient of our electrostatic potential. So by multiplying certain thickness, we can have this voltage difference. Good, but here we have a quantity measured at the oxide field, but we don't want to have this one. Instead of it, we wanted to express something corresponding to the silicon electric field, and this expression gives us quite a good conversion ratio between our oxide electric field and silicon electric field. How can you convert the oxide electric field into the silicon electric field? It is quite easy. Tox is just given here, and this oxide is given by something like silicon oxide. So are you with me? Because I just applied the equation 2.173 directly, so now you can have this expression. So happen to be permittivity of silicon is 3 times higher than oxide permittivity. So relative permittivity is 11.7 and this is 3.9. So their ratio is around 3. So we can say that E silicon. So let me just write down once again. If we accept this second condition, then now we can write down the MOS equation once again. So I wanted to write down in this way. Gate voltage minus flat band voltage. This is a left hand side term, so nothing new, and it is given as phi s plus, what is it, 3 times, of course this 3 is related to the, how can I say, the permittivity ratio. So if you consider different material system, then of course you have to have a different number, and TOX, and here we have silicon electric field. Nothing has changed. I just express Vox, oxide potential, in terms of silicon electric field. The magic comes from now on. So if we can express this silicon electric field in terms of phi sub s, let's assume, if we find an expression of a silicon electric field in terms of surface potential, then now this MOS equation itself can be regarded as just one equation for one unknown variable. What is that unknown variable? As you can see here, this is surface potential. That's the point. So how can we analyze this MOS system electrically? So that is nothing but just apply MOS equation. MOS equation is nothing but just dividing the overall band bending into region-wise sense, and the key is finding out the relation between surface electric field and surface potential, the quantity. Then maybe you can ask me this question. Well, what's the problem? So surface electric field is given as just gradient of electrostatic potential evaluated at surface. That's it. So some of you wanted to write down this way. Well, professor, so I think that it is quite easy. D phi s over dx. This is the definition of electric field. So taking the gradient and taking minus, and that's it. But please try to make point out the long argument of my previous discussion. Why it is not true? Why this is a long discussion? Please note that surface potential is not a quantity dependent on position. When you have a look at the definition of your surface potential, there is no input argument of x. This is just a number. This is not a function. So therefore, you never can take the derivative of this quantity with respect to x. Of course, you can do it, then it becomes just 0. So no information available. So what is actually true in this case is phi silicon electric field as surface is given as d phi dx evaluated at x equal to 0. That's true. Yes, if you can find the potential itself as a function of position, then you can use it. But what we want you to do is don't want to evaluate the exact form of your electrostatic potential nearby this surface region. Instead of that, you wanted to have just a functional dependence between silicon electric field, surface electric field, and surface potential. That's the reason why although they have in more general sense, electric field and electrostatic potential have the simple derivation relation, but it is not available in our case. So now I hope that all of you guys in this lecture now understand the key modeling aspect or goal of this system is this expression. How can we express the electric field only using surface potential? That is the key point. And as I told you before, although we have a lot of different MOS system, but analytic solutions are not available in general. There are only two special cases we have analytic solution, and that first case is now planar MOSFET. We will see from now on. And as I told you before, there is another second and last available system, that is double gate MOSFET with Na equal to 0. Means that there is no doping density at all. So these two cases are available in terms of analytic analysis. Okay, so are you with me? Now let's go to this equation. So the reason why I spent almost 30 minutes to review this property is you have to have strong motivation about finding out the expression. Why we have to consider the relation between surface electric field and surface potential. The motivation is to solve MOS equation, and by solving MOS equation, now we can find out the full understanding on this MOS equation, at least in terms of its electrical property. Of course, we cannot talk about mechanical property or other chemical, physical, we cannot say so. However, in terms of electrical property, that's the equation we have to consider. Okay, so I think that we have already covered this TCAD example, so I want to just skip this one and let's go to simply go to this case. This is a flat band case. In the case of a flat band, we have a really flat band, flat conduction band and flat valence band, and there is no electric field at all. But now when we apply gate voltage, for example, equal to 0.0 volt, although the number is 0, but already in this case we have a bending. So you can see that here we have already certain bending. And when you have a look at actually these two quantities, yes, so you know that this energy difference is corresponding to minus Q times phi S. Well, so although we have applied almost 1 electron volt overall bending for this entire system, actually 0.94 electron volts in entire system, but you can see that the amount of applied to our silicon layer is not fully consistent with 0.94. Please try to estimate it. This is number 1 eV, and this is number 0 eV, and 1 tick is maybe, if I'm not wrong, so 1 tick is corresponding to 0.1 eV. So you can see that 1, 2, 3, 4, 5, 6, not 7. So means that although you have the overall bending of 0.94, about 0.3 eV is applied to the oxide layer, and remaining part is applied to this silicon layer. This is the situation. And now let's go to the even higher gate bias voltage. Then you can see that now Vg minus V flat band now becomes 1.94, almost 2 volt. And what happens in this case? Now you can see that this surface potential almost becomes zero, not potential, surface conduction band energy is almost becomes 1 eV, and here we have almost 1 eV. So 1 eV is applied to our silicon, and the remaining part will be applied to oxide field. So this is, if we have such kind of behavior, then we can say that this is inversion. Why we can say it is inversion? So you know, this is Fermi level, and green one is corresponding to the conduction band energy, conduction band minimum. So it means that nearby this interface, now conduction band and Fermi level are almost aligned. It means that we have a lot of electrons found at that point. Although this system is in its construction p-type substrate, therefore we expect the existence of a lot of excessive holes, but in this system actually applied with 1.0 volt, you can find so many electrons instead of so many holes. This is counterintuitive, so that's the reason why our ancestors named it as a phenomena called as inversion. So I expected a lot of holes, but I found a lot of electrons. Maybe it seems like they internally change their type. Type inversion happens. So that's the reason why they called it as inversion. Okay. So although we will not talk about the accumulation not much, but please have a look at this, the opposite case. In this case, we have applied, instead of a positive gate bias, we have applied minus 2 volt. So usually we don't apply such a negative voltage to our system. But anyway, let's assume. Then what will happen? Usually we expect downward bending of our energy band diagram. But in this case, now we have upward bending to our energy band. But there is a little difference between this minus 2 volt case and 0 volt case. Please have a look at this one. Our flat band voltage in this particular example is minus 0.4 volt. And when we consider 0 volt, the difference is 0.94. And when we consider minus 2 volt, what is the difference? This difference is corresponding to 1.06 volt, more and less the same, so about 1 electron volt. So please try to make a comparison between our case 2 and case 4 simultaneously. So I will just the scale. So now you can see there is a case 2 and case 4. So from my viewpoint, it looks like this. Here previously we had a flat band, and now I applied 1 eV downward or 1 eV upward. And please try to make a comparison between this energy band diagram and this energy band diagram. Although our additional voltage in its absolute magnitude are quite similar, 0.94, 1.06 doesn't change much, but please try to feel something. What is it? When you have a look at case number 2, you feel that, oh, there is a considerable bending. And when you have a look at case number 4, then what is your feeling? Is it much upward bended or just only slightly bended? Of course, your answer will be in contrast to case number 2. Case number 4 shows only marginal change of our bend diagram. So why that happens? So it is because already in this case number 4, small change in our band diagram will provide sufficient amount of hole density into our system. However, if we come back to our case number 2, although we have significant change in our energy band diagram, but that does not provide sufficient amount of electron density. That is the key difference, because please note that both of electron density and hole density follows this term, Ni exponential phi over summer voltage, and also hole density also follows exponential dependence over our electrostatic potential. So when you introduce additional voltage into your system, let's say that potential is slightly deviated by amount of delta phi and delta phi, then it can be decomposed into two terms. One term is without delta phi and times phi kBT over Q. And you can see that also same can happen, and exponential minus delta phi over kBT over Q. So when we have same amount of delta phi into our system, whether that is huge difference or not really depends on our current electron density and our current hole density. So are you with me? I mean that if we have so many electrons already, then if we change a little voltage, then that will introduce huge amount of electron density increase. However, if we have almost 0 electron volt, then the increase of our potential will not give us many difference. Let me just give you concrete number. Let's say that our electron density has two different extreme values. One value is 10 to the 20 per cubic centimeter, and another case is just 1 per cubic centimeter. Of course, in reality, they can happen. And right now, these are the cases. And now I apply just delta phi equal to just 1 millivolt. 1 millivolt, 0.001 volt difference. Then I would like to the new electron density. What is the new electron density? That will be given by 10 to the 20 per cubic centimeter times 0.04. So we will find 4 times 10 to the 18 per cubic centimeter, of course having the original one. So I have to say that the change, increase of delta n will be given as this quite high number. But if we have just 1 per cubic centimeter, then our delta n will be just 0.04 per cubic centimeter. Why we have such a difference? Because in the first case we have already a lot of electrons, and the second case we have almost no electrons. So although potential has changed the same amount, 1 millivolt, but depending on the case, so you have different numbers. So let's say that another case. Well, it's like this. You are a rich guy and you are a poor guy. So you have, for example, you have 10,000 stocks in your pocket, and you have just one stock in your pocket. Then, fortunately, today, in this morning, your stock price becomes doubled. Wow, you're quite happy. But what will happen? Both of them will see that, oh, my stock price becomes doubled. But if we consider actual Korean won earned by them, you will find that there is 1,000 difference between them. Quite similarly, although when we have same amount of potential difference, that introduce same amount of increasing factor for your electron density. But if you already have many electrons, then increase will be huge because the starting point is quite high. And if you have no electron, then almost no electron, that will be quite small. So you can understand this one. In this case, since you have almost no electron at the beginning, so although you have changed a lot of potential or energy bending, but increase of your electron density is really marginal. However, when you have a look at this case number 4, accumulation case, already you have so many holes inside it. So when you change your potential a little bit, then you can provide sufficient amount of excessive holes into your system, so you don't have to have large band bending in your system. Why I'm emphasizing this seemingly obvious argument? This is quite important to understand behavior of your MOS system. Behavior of your MOS system with respect to additional voltage really depends on the current status of your system. I mean that when you apply just gate voltage equal to 0 and gate voltage equal to 1 volt, and now additionally apply 0.001 volt, 1 millivolt, and also apply 1 millivolt to your system. Although the same system, but when it is biased differently, then already these two systems have different number of electrons in it. So if it has already so many electrons in it, then small changes in your voltage will introduce a lot of electron density increase. However, if you don't have much electron density in it, then you will have quite a small increase of your electron density. This is a key point to understand the behavior of your silicon electron density. Please, I will revisit once again with numbers or equations. Okay, so now let's start today's main lecture. This equation is really important, so I strongly recommend it to you to derive this equation by yourself. It is really important. So of course, in this lecture, in this semester, we will see so many important equations. But I can say that as much as MOS system is involved, then MOS equation and the equation we will see from now on, both of them or two of them are the most important ones. So, okay. Any question before starting tons of equations? Okay, then If you don't have any question, then let's come back. Please note that once again, our goal is to derive the expression between silicon electric field measured as surface and surface potential. We wanted to derive this quantity. And you know, since this is related to the electric field, the starting point should be the Poisson equation. So I hope that all of you have already seen this Poisson equation in your electromagnetics course, especially in the electrostatic part, but I will just repeat once again. Although it is quite frequently called as a Poisson equation, however, in general case, this is not the Poisson equation. Well, anyway, let's say that this is a common name for our Poisson equation, and Poisson equation itself is obtained from its mathematical form, but its physical form is nothing but Coulomb's law. So this is nothing but, although we say Poisson equation, but this is just shows that Coulomb's law. Coulomb's law means that, or Poisson equation means that, yes, this is a so simple equation. Let me just state in plain English. If we have net charge density, then that introduce that is working as a source of displacement vector. If there is no net charge density, then there will be no displacement vector. This is the case. So let me just write down more suitable form for our own purpose. You know, this is generally valid for three-dimensional case, but our system is just one-dimensional. So instead of this divergence of a vector, so let me just write down in this way. X-directional displacement vector and its x-directional first order derivative becomes rho. So are you with me? And you know what is the displacement vector? This displacement vector can be obtained by the product between permittivity and electric field. So let me just write down permittivity and electric field. But fortunately, in this case, we are now just considering silicon only. Oh, we have oxide? Yes, but for a while, just to forget about oxide. How can we do that? Because, you know, consideration of oxide part can be done with this guy takes all for our oxide layer. Just to consider only silicon part. Then what we can say is now, where are we now? What we can say now is, here in general permittivity can be a function of a position, but safely we can say this is silicon. And this is position dependent electric field. So yes, so silicon permittivity is constant, so silicon and dE over dx, that is equal to rho. That's it. This is the form of a Poisson equation. Then why we have a little bit strange form here, although this is the form we have derived up to now. Yes, up to now we have derived this form. Let me just give you a further manipulation. So we have electric field, and this electric field, x-directional electric field, is given as minus d phi over dx. It is obtained from the electric field vector is given as minus gradient of electrostatic potential. This is electrostatic approximation for electric field, and by reducing its dimensionality from 3D to 1D, we can easily have this x-directional relation. So if we insert this expression, then now we will have minus epsilon silicon, and the second derivative of our electrostatic potential becomes minus rho. So are you with me? Then if we go to a little bit further, then now we can say second derivative of our electrostatic potential becomes just epsilon. Oh, why do we have here minus sign? So here we no minus sign, and now it is the form of our Poisson equation. Then the next part is, how can we express this net charge density inside the silicon layer? If we are talking about the oxide layer, we can safely say, oh, this is 0. However, as I told you before, we have to consider silicon, and silicon, we have many different sources for our electric charge. So let me just name them. One is Na, acceptor doping. When we have acceptor doping, of course acceptor provide us what? Holes, and instead of that, acceptor itself becomes negatively charged because it was neutral. However, it provides positive charge, so it is negatively charged. So we have negatively charged acceptor doping. And if we have holes, then this is positively charged. And although we have a small number of electrons inside this system, but anyway, we will have electron density, and it is negatively charged. These three are main contributor to the net charge density inside the silicon. Maybe you can ask me, how about the donors? Yes, since right now we are considering N MOSFET, so we will assume that there is no donuts and there are only p-type dopants. Of course, you can add it if you want. So let me just write down. Now we have 1 over epsilon, and now we have to write down Q or rho here. Then how can we write down the net charge density rho? We have contributions from acceptors. Yes. And also we can have contribution from holes. And also we can have contribution from electrons. Point is, they have different signs. Please note that they have different signs. For example, in the case of holes, they are charged with a positive Q. And in the case of electrons, of course, they are charged with minus Q. And in the case of ionized acceptors, they are also charged with minus Q. Okay, so this is the expression. So that's the reason why. So now let's have a look at the final form, Professor Tower's equation. So all of these three factors of three terms have common factor Q, Q, Q. So that can be just pulled out and you can find Q. And now you have P minus N and minus NA. It is originated from Q, P, N, NA. So now you understand. Although there is no solution for this Poisson equation, but at least you can understand this is just Poisson equation we have to consider. Why do we have this specific form? We have made some approximations. 1D approximation. Yes, it's completely okay. And constantness of our silicon permittivity. Yes, also you can say this is true. And also you have introduced another one, like there are hole density, electron density, and acceptor density to contribute to net charge density. Okay, this is also completely okay. So up to now, you have not introduced much approximation for this simple 1D system. If you can solve this equation, then you will get, as a solution, you will find the potential as a function of position, also electron density, hole density as a function of position. Ooh, good, great. But unfortunately, solving this kind of Poisson equation, it is really elaborated. We need a computer program. So that's the problem. So in general, we cannot solve it. But as I told you repeatedly, fortunately for this system, although we cannot solve it numerically, but we can find out valuable information out of it. This is the beauty of this planar MOS system. I really love this system because so we can avoid the use of a computer program. Okay, so please feel free to interrupt me whenever you have any question, because I fully understand to some of you this presentation is not kind enough, because some of you are not fully prepared for advanced discussion. So it's not your fault. So please raise your hand and ask me question. Okay, so once you understand, this is the one we have to solve. This is the Poisson equation. Now we can start the derivation. So now when we have a look at this Poisson equation, our goal is to calculate some information about this MOS system, but well, although we wanted to know something about phi, actually, to be more honest, what we want to get is not solving the entire position dependent phi, but what we wanted to get is just these two quantities. Phi equal to phi at x equal to 0. Surface potential. Of course, once we know it, then by taking this x equal to minus positive infinity, this is a known factor, known number, so we can calculate phi s. And another one we wanted to calculate is just d phi over dx evaluated at x equal to 0. What is it? This is corresponding to the surface electric field. If we just add a minus sign here, then this is just electric field at silicon surface. So we wanted to just these two numbers, but Poisson equation itself provides us another complication. Oh, hole density. Oh, electron density. We just want to know electrostatic potential, but if you wanted to know electrostatic potential, you have to also know hole density and electron density. That's the problem. But fortunately, you have a strong relation. Yes. Do you remember? Electron density and hole density, both of them are exponentially dependent on the electrostatic potential. We have seen it before quite many times, so we will use this expression. So simply speaking, when you come back here, although P is written here, but it can be expressed as exponential phi kBt over q minus. And although here we have n, but it can be expressed as just exponential positive phi kBt over q with some leading coefficient to fit the exact number. Okay, so functional dependence is nothing but just exponential dependence on the electrostatic potential. So let me just do it. Okay. Yes, but but here we have to be a little bit careful. So as I told you before, surface potential is not the potential itself, but reference to the one at far away from this surface, and substrate potential becomes the reference of this surface potential. So therefore we do the same thing. I mean that so okay, let me just slow down and explain it again and again. Here, this is the general expression we will follow, phi. However, we don't want to use this phi exactly, because the reference of phi is preferred to be phi at infinity. We wanted to have this number. So of course, if you introduce this minus phi, then you just destroy everything. So you should compensate it by just adding it once again. Yes, then this is still true, because you have just introduced minus phi infinity and plus phi infinity. They can be cancelled out and nothing has changed. And now you can see that this one, our electron density can be expressed as Ni times, so kBt over q, and phi at infinity. This term is consumed here, and now here we have exponential. Now phi minus phi infinity divided by summer voltage. So are you with me? Then let's just following Professor Tower's notation. This quantity is just called as phi for a while. So sorry about that. So as I told you before, if I am allowed to write down my own textbook, then I will not use this kind of shaped notation. But please note that anyhow we have to follow the majority. So let's say that for a while this becomes the potential. Then now this phi is no longer electrostatic potential itself, but the difference of electrostatic potential referenced to the substrate. Then now please have a look at this leading coefficient. How does it look like? Intrinsic carrier density times exponential phi at p substrate. This expression itself just looks like an electron density expression, but measured at what? Where? Measured at x equal to infinity. Where can you find x equal to infinity? Deep substrate. Simply speaking, this boxed quantity is nothing but the electron density which can be found at the deep substrate. So simply speaking, this becomes electron density at x equal to infinity. As you know, this number would be extremely small. For example, if our acceptor density is 10 to the 17 per cubic centimeter, then this n at infinity will be just 10 to the 3 per cubic centimeter. That number is extremely small. Please note that this coefficient is so small. This is really important. So, well, let's come back. We can follow the same argument for our Hall density. So now we can find this modified equation. These two modified equations, you can find still phi and phi. Although you can find phi, this phi should be regarded as, in our original terminology, phi x minus phi infinite. So sorry about that, but you have to follow this one. Then please make a comparison between this red colored one and blue colored one. In red colored expressions, we have the balanced leading coefficient Ni and Ni for holes and electrons. Both of them have just 10 to the 10 per cubic centimeter. However, when you have a look at this one, then what you can get is, this is at most 10 to the 3 per cubic centimeter, and this one is 10 to the 17 per cubic centimeter if our acceptor density is 10 to the 17. In other words, this P at infinity is corresponding to Na, and this N, electron density at positive infinity, becomes Ni square divided by Na. And many cases this number is extremely small and this number is extremely high, large number. So there are several orders of magnitude difference between this P and N. Now let's say one thing. Let me just give you one thing. Previously we had phi, a certain phi at certain position. Now instead of this potential at a given position, let's assume that by some mean now we have small difference in its potential. Then what will happen to our electron density and hole density at the same time? If we change it just to 1 millivolt, then here we have additional 1 millivolt and additional 1 millivolt. Yes, their changing ratio, the ratio of their changing in terms of percentage, is the same for electrons and holes. However, since there are tons of holes already in this part, amount of delta P will be really humongous. However, amount of delta N will be really small, almost negligible. Please understand this difference. From the starting point, we have so many holes, and holes are extremely sensitive to the potential difference. If you change just 1 millivolt, then you will change 10 to the 15, 16, 17 per cubic centimeter can change. However, when holes change so much, at the same time electrons doesn't change much. It is just changing 1,000, 10,000. Difference occurs in this case. So this imbalance between electron density and hole density, or imbalance of sensitivity of electron density and hole density, that is the important factor we have to understand. Well, anyway, using these expressions for holes and electrons, then now we can rewrite the Poisson equation once again. So left hand side is just a second derivative. I have not changed it. And you can see this seemingly quite a complicated number. But please, this is not that difficult. So let me just show you term by term. Na times exponential of minus exponential of our electrostatic potential. What is it? This is corresponding to hole density. And here you can see another factor, Ni squared divided by Na times exponential positive phi. What is it? This is nothing but just electron density. And you have remaining terms like Na minus 1, and here you have Na minus, yes, Na is positive Na. This one is corresponding to the acceptor density. So you have, maybe you can find that, oh, there is a small difference appearing here. Previously we have had, but please check when you come back to your dormitory room. Please check this is the exact equation. So why we have this kind of difference is hole density at far away is not exactly Na. It has small differences. So please check your equation. Anyway, now we have the Poisson equation written in terms of electrostatic potential only. That's the key. Here, Poisson equation, in previous slide, we had 3 unknown variables. One was electrostatic potential, another one hole density and electron density. But now, by using some exponential dependence of electron density and hole density on the electrostatic potential, now please have a look at here phi, once again phi, and once again phi. Is there any electron density? No. Is there any hole density? No. There is only one equation for one unknown variable. So now we can solve this equation. So now we have 2 choices. We have equation and we can just solve it by numerical way. But we will take another way, not exactly solve this equation, but just to do something. This do something, when I say do something, this is a key idea to simplify everything. Actually, even, how can I say, even in my opinion, if you take basic idea about Poisson equation and electron and hole densities inside the semiconductor, you can derive this equation. Up to now, everything is quite straightforward, but the next step is the key invention or key idea to really make our life or our derivation simplified. So please have a look at this key idea. This is the key idea. What is it? So previously we had Poisson equation, and what we do right now is not just integrating Poisson equation, but multiply. What is this? This is just minus times electric field and dx. So we just multiply electric field to the left hand side and right hand side of our Poisson equation. After that, you will find this Poisson equation. Well, previously you had 1 equal to 1. Now you multiply 3 to the left hand side, right side. So now you have 3 equal to 3. Quite similarly, this is your original Poisson equation, and you multiply 3, so this is your multiplied Poisson equation. So let's come back. This is your original Poisson equation, and you just multiply same factor, electric field times dx to the left hand side and right hand side of your Poisson equation. Okay, time is up, so I have to stop now. But let me just emphasize once again. Today, we just review our previous lecture. We have to solve a MOS equation. However, MOS equation has two unknown variables: surface potential, the potential of band bending inside the semiconductor, and oxide one. However, that oxide one can be just converted into electric field, surface electric field. So now our goal is find out the relation between surface electric field and surface potential. In order to find out their relation, we must solve Poisson equation. However, Poisson equation itself cannot be analytically solved in general case. So in order to solve that problem or improve the situation, we just multiply some factors to the Poisson equations left hand side and right hand side. So we will keep this discussion once again, but I hope that already this lecture material is given to you, so please follow the derivation procedure. Since this derivation procedure is so important, I wanted to once again emphasize the importance of this derivation and recommend you to do it by yourself. This is critically important. Okay, thank you for your attention. Bye.